Alright, so now we know how to use the mole ratio. So we're going to look at how that mole ratio plays into other parts of our stoichiometry. Main thing when we're working here, we've seen this part before when we worked with just the mole and grams and atoms or number. We saw that before. The only thing that we've really added is we've added in the mole ratio. Okay, so the way that this works, remember, when you start with mole, you always multiply. If you start with anything else, you're going to divide. So when looking at this, if we start with grams, so say we start right here, and we go from grams to moles, well, we're going to divide by our gram formula mass. Now, the thing that we have here, the addition, what's new is the mole ratio. What the mole ratio allows us to do is to convert between different substances in a chemical equation. So, if I want to go from grams of anything to back to moles of whatever's in the equation, what I can do is go from grams to moles, use the mole ratio, and I can figure out how many moles I have. Now I can go back, so say I wanted to get grams. So I started with grams of a substance, and I wanted to figure out, we'll say this is grams of A, and I wanted to figure out how to convert to grams of B. So A is anything. Okay, it's in a chemical equation. It's the first thing that you start with. It's the number that it gives you. So I can go from grams to moles of A by dividing by my gram formula mass. And then I can use my mole ratio to change to anything else in the equation. So I can go to moles of B, whatever B is. It doesn't matter what it is. And then if I want to go back, so if I'm in moles and I want to go back to grams of B, I just use that gram formula mass and multiply, and I could get grams of B. Okay, basically what this boils down to, anytime you see grams, whatever you see it by, if you see grams, whatever you see it by, or mass or anything like that, you're going to need the gram formula mass. Okay, and then once you get it to moles, you can convert it to anything else in the equation by using the mole ratio. And then again, if I want to get it back in grams, I want to figure out how many grams I have, well, I need the gram formula mass. So anytime I go from grams of something to moles of something, I need the gram formula mass, or if I'm going from moles to grams. Anytime you see grams, whatever it's by, you need that gram formula mass. And then we can always use Avogadro's number to figure out how many atoms or how many molecules that we have. So looking at dimensional analysis again, we're looking at it. Here we have our nitroglycerin, and we're saying that we have 5,000 grams of it. Well, if I want to convert it to something else, I have to use the mole ratio. So it has to be in moles. So I have my 5,000 grams. Remember, if you ever see grams, you need the gram formula mass. Well, the gram formula mass of nitroglycerin is about 227 grams per mole. So that's where we see this relationship. 1 mole equals 227 grams. That's my molar mass. And then here, if I'm converting it into CO2, well, look at my ratio. My ratio is a 1 to 3. So what I see is I have a 1 mole of nitroglycerin for every 3 moles of CO2. My units cancel, and I'm left with a unit of moles of CO2. So all we have to have is, if we start with grams, we need the gram formula mass. And then the mole ratio lets me transition from anything to something else in the equation. So let's look at an example. It says that 50 grams of iron reacts with excess oxygen to form iron 3 oxide. How many moles of iron 3 oxide are produced? So what I'm looking for is moles of iron 3 oxide. What am I starting with? I'm starting with 50 grams of iron. Well, the first thing we need in any stoichiometric conversion is we have to have a balanced chemical equation. Okay, so what do we have? Well, we have our iron reacts with excess oxygen. So iron is Fe. Anytime we write an element, we check, is it a diatomic? Iron is not. Okay, it's reacting with excess oxygen, which is O, which in this case is oxygen a diatomic? Yes, it is. So we put O2. Okay, and it forms iron 3 oxide. So iron, which has a +3 oxidation number, and oxygen, which is -2. So we go ahead, crisscross this. I'm crisscrossing because this is an ionic compound, and we get Fe2O3. So there's my chemical equation. Is it balanced? No, not really. So first, let's start with our metals. How do we balance that out? Well, we can take this. Let's move it kind of in the middle. There we go. Oh, missing that little part of iron. Start with our metals. Yes, we can balance that out really simple and put a 2 right there. But then our oxygens aren't balanced. Okay, and so what we're going to have to come back and do is oxygen we see is a 2 and then there's a 3. Anytime you see a 2 and a 3, normally the common value is going to be a 6. So how do we make 6 oxygens on this side? Well, it's 3, and then we put a 2 right here. Okay, remember that 2 distributes to iron as well. So my oxygen are balanced, but now my irons are 4, so we just put a 4 right there. Okay, so going on with the problem now. Now that we have a balanced chemical equation, we can actually work out the problem. Now remember, I told you, anytime that you see grams, you need the molar mass. Whatever it says grams by. So it said 50 grams of iron. So guess what you're going to need? You're going to need the molar mass of iron, which is right around 56. We'll round it to there. So 1 mole of iron equals 56 grams of iron. Okay. Now, the other thing we need with excess oxygen to form that, how many moles of iron 3 oxide? So we need moles of iron 3 oxide. So anytime we're dealing with stoichiometry, we're going to use the mole ratio. So we're going from grams of iron to moles of iron 3 oxide. So what's our mole ratio? Well, it's a 4 to 2. So 4 moles of iron equals 2 moles of Fe2O3. Okay, those are our conversion factors. We call these over here our statements of equality, and then we just set up our problem. So 50 grams of iron, set it up. Since this says grams of iron, I use my molar mass, 56 grams of iron. Put the other part on top, equals 1 mole of iron. Okay, keep going. And we see that now these units cancel, grams cancel. Now we're in moles, and I'm transitioning and converting from iron to iron 3 oxide, so I need my mole ratio. So for, undo that. So 4 moles of iron would go on the bottom, and our 2 moles of iron 3 oxide would go on top. Cancels it out, and then all I do from here is just multiply out the top. So 50 times 1 times 2, all divided by 56 times 4, which if I multiply it out correctly, I should get something right around 0.446, and that would be moles of our iron 3 oxide. Okay, on our next example, it says an unknown quantity of ammonium phosphate, okay, is reacted with excess barium nitrate to produce 500 grams of ammonium nitrate. How many moles of ammonium phosphate were in the original sample? So when I'm working this one out, I first got to start with my balanced chemical equation. So the first thing I have, my first reactant is ammonium phosphate, which ammonia is NH4 with a positive charge, and phosphate is PO4 with a -3 charge. We crisscross and we get our NH4 3 and our PO4, which we take that guy, and that's our first reactant that we have. Okay, and that's reacting with our barium nitrate, which barium is Ba, and barium has a +2 oxidation number, so it'll be 2 plus, and then is bonded to nitrate, which is NO3, negative charge, crisscross, and we get our BaNO3 2. Okay, so those two guys are reacting together. Okay, and they go ahead and they produce out our two products. It's a double replacement reaction. So our two products are going to be, the first one is ammonium nitrate. So NH4, positive charge, NO3, negative charge, crisscross, and we get NH4NO3. Okay, plus our other one is going to be our barium will now be bonded to our phosphate. So barium is Ba, 2 plus, phosphate PO4, 3 minus, crisscross, and we get Ba3PO4, 2. Okay, there's our chemical equation. Now all we have to do is balance that guy out. So when we balance this out, looking at it, let's start with our metals first. So we have our barium, which, do these a different color. Barium, we have 1 here, 3 there. So to make that, we put a 3. Okay, now we have to balance out our ions. We see that phosphate is 2 right here, but we see that nitrate, that's going to be 2 times 3 is 6. So we can balance that out first. Either one, it really doesn't matter. We'll put a 6 right here to balance out the nitrates, and our ammonium needs to be 6, and our phosphate needs to be 2, so we'll put a 2 right there. So we get our nice, neat, balanced equation, which will give us our mole ratios, which we'll need a lot later. So let's look at what we're starting with. In the problem, we're starting with 500 grams of ammonium nitrate. So we have our 500 grams of our ammonium nitrate, which that's NH4NO3. That's what we're starting with. Okay, so let's look at the rest of the problem. So we know we're starting with that, and we want to figure out how many moles of ammonium phosphate were originally in the sample. So here is our ammonium phosphate. So we have 500 grams of ammonium nitrate. Anytime we see grams, what do we need? We need the molar mass. So we're going to write that one down first, and we get our molar mass of our ammonium nitrate is right around 1 mole of ammonium nitrate, which is NH4NO3, is right around 80 grams. Well, not 8 grams, but 80 grams of NH4NO3. Okay, the other thing that we always need our mole ratio. So what's our mole ratio between these two guys? It is a 2 to 6. So 2 moles of our ammonia phosphate equals 6 moles of our NH4NO3. Okay, so now that we have everything set up, we can set it up in our stoichiometric relationship or dimensional analysis over here. So 80 grams goes on the bottom. That equals 1 mole, which goes on the top. Continue it on out because we want, now that we have it in moles, we can now convert into our moles of ammonium phosphate. So we go ahead and we see that moles of that 6 go on the bottom because that's what we originally have. That goes up on the top, and we see that we just go ahead and we multiply it out, and we'll just go ahead and multiply it out, which are 500 times our 2, all divided by 80 times 6, which should give us right around 2.08, and that would be moles of our ammonium phosphate.